across all moduli suitable for the transform for length. Note. So, okay, so this function goes through and tries to find moduli. Basically, here's what it's doing. You give it a function f, lowercase f, which takes just a number like m, and you choose what to do with this. So you choose. You can see it as a callback of sorts. It's going to choose all m that has a factor, which is written like this, 2 to the L, where L is our transform length. Sorry, this whole thing is our transform length. Of course, there's an infinite number of primes that are going to satisfy this. So this function is going to run forever, actually. So it's our goal to quit out when we're done, when we find everything that we want to find. So let's change map suitable moduli, and so find suitable moduli would be something like this. So f let count be 0, count is within here. We already have count, and our moduli is a nil list. So we are map suitable moduli, our function f on our transform length. And then we return our moduli. That's all this function is going to do. So decf let's see, push. So we want to push m onto our moduli, push m moduli. Like I said, fm is this thing that can do anything. Here we're collecting them, we're pushing them onto our list of moduli. We're decrementing m, and when we reach, decrement count, when we reach a 0 count, count is integer. So when we reach a 0 count, then we bail out. Return from with our value moduli. So let's see what this refactored version does. If we compile this and we do find suitable moduli, this actually has slightly different semantics than the previous one, but let's try it. Let me do find suitable PHP 258 with a count of yeah. So let's do 10, 100. Yeah, okay, good. Good. So this is good, this is good. And now if we go back to our print, Our print suitable moduli, however, still never mind. It does the right thing. So we have our second version of print suitable moduli up here. Let's write something maximal suitable moduli with a particular word length. So here we give it a particular word length. We are definitely bounded by the number of these that exist. So we're going to do f let f m when so let max modulus, how should I say this? I should say modulus bound. Modulus bound is expt 2 to the 1 plus word length. 1 plus word length. And then that minus 1. So again, that's just saying here that our modulus m has to be less than or equal to 2 to the power of our word length plus 1 minus 1, because this is our maximum representable integer on our platform. So I need to make sure that that's encoded. So our bound, we need to make sure m is less than or equal to our modulus bound. However, now we're checking if it's greater, so when it's greater, then we bail out. So return from suitable moduli. We start a modulus of nil. Our modulus. Set f mod. And set f our modulus to m. So we just keep going on and on and on until we find what we want. So we have a few other things, which is our waste factor. So let waste, we compute that here. Actually, we should just copy this whole thing right here. The width and the waste. So the width is that, the waste is that. We can compute it after we do our bailout check. So we're checking it with m. Our waste is the width minus nth value factor modulus 2. And if it satisfies that, then so when our waste is less than our max waste, less than or equal to our max waste, then we set f it. All right. So let's see. Yeah. Okay, so this looks good. So we delete that. M is going to be our thing. Let's try this out. Maximal suitable moduli for a word length of 64 bits with a max waste of 10, let's say. That did not work as expected. When our waste is less than or equal to yeah, okay, of course. this isn't actually doing anything. I just wrote the function to do it. Map suitable moduli. Our function is f, and our transform length. Let's say is 2 to the floor word length 2. So start early with so what we're doing here is we're calling map suitable moduli. Okay, so if we have our word length w, we're going to start by finding moduli which divide. We're going to compute the set of moduli that divide. How do I explain it? 2 to the word length divided by 2. That'll kind of maximize our. This will start the search very low. So this is going to be our assumed X-form length. But we want to find numbers which kind of saturate this. Ideally, we find numbers that are approximately, that divide 2 to the W. So let's see how this works. Maximal suitable moduli of a word length of 64. Max waste of 5 bits. Actually, this is probably going to take a super long time now that I think about it. So I actually want to search for. Oh, okay, yes. So how should I do this? For L from word length down to 1, do map moduli. Okay, so I think this is going to be, oops, again I made an error. From L. Okay. So I'm going to step from the maximal modulus. So if I go back to here, I said I was going to do this w divided by 2 stuff. I'm not, whoops. I am not going to do, how did I do that? I have no idea how it's zooming. Oh, it's multi-touch or something like that. Let me, I need to disable that. I'm not doing this stuff anymore. What I'm going to do is start looking for transforms that are 2 to the word length and see if I can find any moduli that satisfy that. If not, I'm going to go w minus 1, w minus 2, and so on and so forth until I find a modulus that satisfies that. And that modulus is guaranteed to be maximal with the least wastage. So, but the control structure here I need to be careful with. Let's see, how should I do this? Let's do catch retry.